All right. So in this particular talk, we are going to talk about now the scattering. Remember, previously we did a lot of work on the Fresnel equations and, on the incidence and clear points, right? And we said that, okay, which one is the incident first point, first order refraction, this glare point, which is first order refraction. And this is the incident and the glare point of reflection. And this is how you have illuminated this particle using a monochromatic beam, for example, so at an angle. So the large particle images point onto the detector to the clear point. We already did. Now let us look at scattering according to geometric optics. Now, say for example, you have a particle and you have an incident monochromatic light, and only a part of it is basically shown, and this is the surrounding media. And so the geometric optics basically describes the light scattering from small particles using the laws of reflection and refraction. So this statement you should very clearly pay attention to, that it is nothing but it describes the light scattering from small particles using the laws of reflection and refraction, which we already did in details. Uh, so the assumptions are usually made that the particle is spherical and the incident light is monochromatic, which is in the case of a laser, for example. And subsequently, what you do is that you allow Snell's law and Fresnel equations are used to compute the reflection and transmission angles and intensities. Okay. So Snell's law and Fresnel equations are used to compute the reflection and transmission angles, and we already saw how you can calculate the power as well. So looking at this particular scenario, let's take one incident beam, which is given, incident ray, which is shown in this particular color. Now, part of it is, of course, reflected. This is reflected, okay? And then part of it is refracted. So where it comes out, it's basically the first order refraction. And then a part of it is again gets reflected from this interface. Then it comes out to the other side, which is called the second order refraction. And this goes on and on. Okay? The cycle kind of goes on and on. You can understand that the incident beam, incident ray, if part of it is reflected, part of it goes in, and then whatever comes out through the other side is basically first order refraction. Then whatever comes out through this side is second order refraction, and then it goes on and on and on and on. Okay. Each time the intensity is lowered, as you can see, and but this is a very prominent thing that happens. So whatever the detector measures is a combination of all these things that basically comes out of this particular situation. Okay. So light scattering from small particles are considered under the following assumptions that, there is a plane incident wave and there is a homogeneous particle matter. Basically, this is the particle matter and it is a spherical particle. So the exact solutions were given by, by me, or what we call the Lorentz-Mean theory. What happens is that there is an incident wave which falls onto this particular particle, and there is a lot of scattered wave in all directions. You can see these are the scattered wave fronts in all directions. They are not equal in all directions, by the way. So there is an incident wave that lands on a particle of a homogeneous particle material, which is spherical, and this is a plane incident wave. This gives rise to this scattered wave, which are basically scattering in all possible directions, not equally though. So the exact solutions of these problems are given by the Lorentz-Mean theory. So here you can calculate using ray optics, using geometric optics. You can calculate all these, how much light is reflected, refracted, etc., etc. But it is much easier to use the waves and calculate it from the, from the Lorentz-Mean theory. Okay. So from geometric perspective, optics perspective, it is easier to understand that what may have gone on. Why do you get multiple glare points? and what is meant by first order and second order refractions, and so on and so forth. All right. So this is what happens, that when you talk about Lorentz-Mees scattering, so the scattering of a plane wave by a spherical particle is described fully by the Lorentz-Mees theory. Okay. So it is basically how a plane wave is scattered by a spherical particle. Okay. So the scattering is governed by what we call the Mie parameter, which is a non-dimensional diameter. It is nothing but the diameter divided by the wavelength of the illumination multiplied by pi. So essentially it is proportional to the diameter of the particle, but there is an inverse catch on the wavelength. Okay. And this is a function of the relative refractive index, which is NP by NM. Okay. So the scattering is characteristics of the different ranges of the Mie parameter. So when the Mie parameter is less than 0.2, okay, which is less than 0.2. So if you invert it, you will see it is less than the lambda by pi, which is less than 0.2 of lambda by pi. Okay. So when it is less than lambda by pi, when it is basically the particle, this essentially means when the particle diameter is less than about 0.2 of the wavelength divided by pi. Okay, so that means very small particles. Essentially what we have was called the Rayleigh scattering. And then we go into the Mie region, where the particle, or the non-dimensional Mie parameter, is between 0.2 and 10. And then we go to the geometrical optics range when xm is much greater than 10. So if you look at it in this particular plot over here, for example, the lambda that is used is 488 nanometer, can be anything else. And this is the Mie parameter that we have plotted. So when the Mie parameter is, less than, say, about when the particle diameter is really small. So this is the particle diameter, because once you know the wavelength, you can also plot the particle diameter. So when the particle diameter is about 0.1 to 0.2 micrometer, which means essentially that it is 100 to 200 nanometers. Okay, this is for this particular wavelength. You have what we call the Rayleigh scattering, and this is measured at 30 degree. This is measured at 90 degree scattering angles. This is the measurement. So as you can see, the signal is pretty low, very, very low. The arbitrary intensity profile is somewhere around 10 to the power of minus 14 and ranges up to about 10 to the power of 8-ish. Okay? And when you do it at 90 degrees, this is even lower. Okay? As you can see, this goes down pretty fast. The low particle sizes, as you can see, the scattering cross-section is pretty small, and the intensity that it scatters at different scattering angles is also pretty small. Then you go actually to the Mie range, which is between about 0.2 to all the way up to about 10 microns in size. Okay? So if you look at this particular range, you see these lobes. We will discuss about these lobes. These are due to interference. So these lobes you get over there. So up to about 10 microns in size. The intensity is pretty high, much, much higher. Actually, it is about 10 orders higher than this. And then if you go to the geometric optics range, this is very high. That means up to about 100 microns. This is very high. So the idea is here the intensity scales are somewhat about x to the power of 6. Here it is up to x to the power of 2. Okay, so this is the kind of ranges that we are actually looking at. Okay, so this scattering characteristics is the power for is characteristic for 3 different ranges of the Mie parameter. So this is the important part. This will come in very handy later on. This is given for a particular wavelength. Remember that. All right. So so this is Rayleigh scattering, Mie scattering, and then you go to the geometric optics. Okay. Now, if you look at now, say that there is a relative refractive index, say is about 1.4, and then you look at, just look at the red line for the time being. So this is the diffraction and reflection. Okay, so as you can see over here, and this is how the intensity actually varies for different scattering angles. Okay, and this is the region actually where we will see that we will conduct the phase Doppler anemometry, which is around scattering angle of this region. Okay? So this is how the scattering, the diffraction, and the reflection happens. Okay, remember that is how we are kind of trying to understand this. Okay, similarly, if you look at first order refraction, so this was reflection and diffraction. This is if you look at first order refraction. Okay, what you can see is that this is the phase Doppler region. Okay, and this is how the refraction happens. So this is what actually comes out. Okay, and this is the incident part. Okay, and then the relative refractive index is basically the same. Okay, so this is how the relative profiles actually. So this is the reflection part. This is basically the first order refraction. If you look at it carefully, you will see that basically these two are basically similar. Got it? Okay. Now, if you look at from a geometric optics perspective, so the scattered light at any particular scattering angle contains different scattering orders. It contains the scattered light, as we see, it has different already we know from the geometric optics that scattering is composed of everything: reflection, refraction, all orders of refraction, etc., etc. So if you look at this is an incident wave and this is a particle, so you get this is the incident wave, which are in orange, and then you have reflection, which is marked as green. Then you have first order refraction, green but of a different color. Then this is of a second order refraction. Okay, and then you get third order refraction. Well, okay, so second order and third order refraction. So it is composed of reflection, and then you also have diffraction because of the particles that we already covered, that you get those airy disks and stuff like that. So reflection, first order refraction, second order refraction, third order refraction, all these things are contained when actually light is scattered at any particular scattering angle. It contains different scattering orders, therefore. This we already saw from the geometric optics point of view. Okay, and this is kind of summarized by this particular diagram that you see over here. Okay, so I will just hover on this for a few seconds, where you can just make sure that you have got everything here. So when you talk about light scattering by small particles, this is a pretty complicated diagram that you can see over here. So this is for parallel polarization and this is for perpendicular polarization, which we already know by now. So this is diffraction. Okay, and then this is first order refraction. This is reflection that you see over here. This guy that you see, this one in kind of bluish color, this is third order refraction. Okay, and this is second order refraction. Okay, and it's a mess. So this is the second rainbow and the first rainbow. This is for monochromatic light, remember. So this is not conventional rainbow, that what you know from your high school physics perhaps. This is second order refraction, and this is obviously the Brewster's angle over here, where it goes to 0. This Brewster's angle you can also see here, okay, where reflection is actually equal to 0. So this is the same Brewster's angle, which we covered a few in the last lecture, basically. So you can see it. So there is this, this is for perpendicular polarization. So here the scatter. So at different scattering angles, you get to see, different domination of different scattering modes. And you should remember that all these lobes that you see over here, they happen because of the interference among the scattering modes. So that is also important. That's why you get this very funny looking characteristics. This is Alexander's dark brand, named after Alexander the Great. So as you can see, perpendicular polarization has a particular kind of scattering patterns, and parallel polarization also has a kind of a pattern. And all the orders of refractions are written over here. For example, first order refraction goes down to 0 after 90 degrees, that you can see right over here. Reflection continues for a while, okay, and second order refraction picks up after you are at a certain scattering angle. Okay, so you can see all of this kind of makes pretty common sense if you think about it, of a particle. And if you think about after 90 degree, there cannot be any first order refraction, or the probability of that will decrease quite a bit. Okay, and this is the dependence on the relative refractive index, and you can see these are looks all pretty complicated, but this is. So again, so we know once again to harp that this is nothing but, the scattering from small particles that we are looking at it over here. And this is once again the Lorentz-Mees scattering. If you just go back to this particular slide once again, which I wanted to show that, depending on which where you are actually monitoring it, it varies quite a bit. And it also depends on the particle sizes that you are trying to measure. This is the most important graph that you can have. So if you do a polar representation of the scattered light, you will find that when dp is small, that is, it's roughly in that Rayleigh scattering limit, and this is the direction of illumination, the kind of scattered intensity you get. Okay? As you go on to 1, about the wavelength, you get this kind of multi-lobe featured. As you can see, forward scattering gives you much more intensity than backward scattering. And then if you go to 10, you get all these, very intricate lobes. Here also the forward scattering is much more than the backward scattering. But advantage is that backward scattering, if you monitor, even though it is lower than forward scattering, you can integrate the optics and get rid of the alignment delays. Okay? So these are all shown in logarithmic scale. So the polar diagram is a function of the scattering angle. And not only scattering angle, the forward scattering is always more than the backward scattering. And these lobes, once again, these lobes we said are due to what we call the interference, right? Interference, so the rainbows, okay. For explanation of rainbows lies in the fact that for higher scattering orders, the direction of the scattered wave reverses as the incident angle changes. The angle at which reversal occurs is known as the rainbow angle. So more about it, you can learn, you can do Google search, you can learn about more about this later. So again, just hold on and see that this is once again the same plot. Just want to re-emphasize that now that it's very important to know what kind of polarization you actually have. So this now moves to what we call the image processing fundamentals. Now that we know that, what is light propagation, what is scattering, and we know a little bit about Lorentz-Mees theory, we know scattering from small particles, we know geometric optics now, we also have known the Snell's law and the Fresnel equations, polarization. We know all about cameras and lens systems now. So now it is an important part to know that what are the image processing that you need to do. As you know, the image detectors comes in two varieties. One is a CCD detector, one is a CMOS detector. The CCD is a charge coupled device. It converts spatial arrangement of accumulated charges into an electrical signal. The CMOS is complementary metal oxide semiconductor with reduced size of transistors. It's possible to give each pixel its preamplifier and additional circuit. So in contrast to a CCD, it is possible to read out a part of the sensor without any speed loss and with the same pixel clock rate. The high-speed camera technologies are therefore dominated by CMOS. High-speed sensors, which are not limited by CMOS technology by the transfer of digital image data. So this is the two types of image detectors that you have. So the images are basically the grayscale images that you see over here have pixels that range from black to white, going through a number of intensity steps in between. So most of the images allows 256 intensity levels. So a number that arises from 256 different values that a byte can take. and a byte is composed of 8 bits. So a byte is composed of 8 bits. Okay, and such images therefore are known as 8-bit grayscale images. Some high-end scanners can also scan with a finer intensity, so they can do like 12-bit or 16-bit and 10-bit, okay, to represent the intensity values. So therefore it makes it possible to go up to 4096, 10024 to 4096, or even 65536 different gray values. Okay, so that is also possible. And 1 bit, if you look at it, is basically 2 gray values, which is essentially a black and white image. Okay, so the some points when you go for 12-bit or 16-bit, okay, is basically the images take up more space, and not all imaging softwares can work with this kind of an arrangement. Okay, so and you might see no difference in the computer screen, because the computers may be only programmed to show up to 256 shades of gray. So that is also another thing that one should keep in mind when you actually are doing this. Okay, and you don't see the dark. Basically, you don't see the dark areas of the gray of the image any better. Okay, so higher, so the number of bits that is used for intensity values is also known as the bit depth. So higher bit depth, which is what you have for 12-bit and 16-bit, is not necessarily a great thing. But it is kind of, it's possible to see kind of. Okay? And the pixels also need not be square. They can have angular distortion and also different dimensions, the two directions, and all those stuff. Okay? So this is, for example, the image on a 7-bit scale. Okay, and this is the image on an 8-bit scale. So this is 7-bit, this is 8-bit scale. So you can see the difference. Larger number of representation levels, not here. Okay? And image processing tools, there are quite a few. You can have MATLAB, LaVision. These are proprietary, which normally people use in their labs. There are a number of open source codes as well, like ImageJ, Octave, OpenCV, stuff like that. We'll have a tutorial session on the image processing later, where we will show some of these characteristics. So some of the basic operations are colorization, summation, multiplication, subtraction, averaging of images, thresholding, binarizing, and then filters also. Okay, so all these things are there. So gray images, this is, for example, an 8-bit image. This is another 8-bit image. This is another 8-bit. And so the histogram of gray levels in the image is something like this. You can see that 8-bit can have 56 levels of gray. So, that is what you see over here. Okay, here, for example, you see almost bimodal distribution, because less information, because it is kind of very sharp interface. Here, of course, you see, because the image has got many shades, because it has got many parts, more population in the intermediate gray levels. The peak is still at the minimum level. Okay? And then this is a more complicated image, the car and house and all those things. So the information content is very high. Here it is basically bimodal, because it's like, for example, if you put a particle, so this is just the gray and the background. So this is like kind of almost bimodal. And this is has got all values in the intermediate gray sections, right? Intermediate gray levels. The information content is very, very high. So what you do is that for pointwise operations, you look up table. So mapping of gray value to the brightness value. Okay, this is called LUT. LUT may be linear or non-linear. Okay, non-linear LUT is displayed image will not be exact representation. So the variety of visual effects can be obtained by varying the functional form of the LUT. Okay, so this is and these are other common examples of LUT is brightness. So GU is equal to U plus B. B greater than 0 is brightening, less than 0 is darkening. So you can see this kind of examples. Okay, so this is a LUT brightness example. So this is like brightening, saturation at higher intensity. You have got more saturation, higher intensity values. Okay? So this is all that is there. Okay. This is, for example, darkening, like saturation, lower intensity, in an example of an LUT. There are also point-wise operations that you can do. That a common example of an LUT will be MU plus B. M can be high contrast or low contrast, etc., so that the images can be passed through multiple LUTs. So these are kind of image processings that one can do. This is a contrast example. So this is enhancing the contrast. So saturation at limited intensity, limiting. Okay, so these are some of the finer examples that one can. These are more of the same. We are not going to go into the details. There are also auto scaling examples, that contrast enhancement, where you set minimum gray value as black and maximum as white to avoid saturation at black and white. So alternate is that set 1% and 99% intensity values as black or white. So this is an example of an auto scaling that you get. The minimum is 125, max 2. Okay. So this is, of course, an inversion. You can just, it makes like common sense what inversion exactly means. There are more point-wise operations. These are gamma correction, for example. It's a non-linear LUT or contrast. Okay. So this you can read more, and we will also have a demo session on this. This is like gamma correction. This is enhanced contrast, no saturation at limiting. So more of the same. This is again a gamma correction. These are different LUTs for contrast enhancements. Okay. All of these things we will show in a couple of slides over there. Okay. In a definite in a laboratory session. So this is, for example, the threshold selection, where we talk about Otsu's algorithm, which selects a threshold that minimizes the sum of intra-class spread, that is the variance, and this is equivalent to maximizing inter-class variance. There are certain examples, for example, here. So this is the image. So if you took the threshold value of 60, and this is the threshold value from Otsu's algorithm. Okay, so this is a very common thing, Otsu's algorithm, that is routinely used. We'll have a demonstration of. Okay, so this is an original image. This is the grayscale image. You do the thresholding of this, and you get what you are seeing over here. Okay. In other words, image processing is important. It helps to decide exposure time, light intensity, aperture, etc. It is essential to determine quantitative data from the images. And these are the books which you can read. This is the Springer Handbook of Fluid Mechanics, and Professor Tropia. And you can read all about the different comparisons of CC cameras. You can look at out of focus effects on particle visibility and correlation. So all of these things are here. There is a lot of material, so feel free to read these materials in your